All right, so let's start. CSTN 283, May 3rd. John Freer, let me get, make sure we're good. We're going to do a course wrap-up. We'll go over Quiz 4. We're going to do a course wrap-up, but just for those of you who are not here, we did just get back from the weatherization test house, the one that we've worked on, the one our project was centered around, and we did our final blower door test on it. And if you remember, we tested it prior to doing any of the weatherization work, and at 50 pascals, we had 2,520 cubic feet per minute. We did, based on a compilation of all the weatherization plans, we did one weatherization improvement plan, kind of took the best things that we could out of all of them, executed all the work, and we just tested out at 1,020, was that it? 1,020. So we actually in a very limited budget, under $500 for materials, with labor just from us in the class, we managed to do about a 60% improvement in the convective air loss in the house. So, I think an excellent example of what can be done, and we really did. We just picked the low-hanging fruit and had significant results. So, good for us. We did good work. The homeowners, I'm sure, will be pleased. So, I guess before we get started, if you don't have anything super specific, I was going to run through the quizzes. We'll talk about those. If they jar your brain for any questions, then we'll talk about that. But let's just start and go quickly through Quiz 4, and then let's find somebody's quiz. Somebody that's not here. So the first one, and I think this was pretty straightforward, we talked about this. Two auditors perform the test on the same day with the same conditions with the same blower door. One of them came up with the result of, they both got the same result, 1,586 cubic feet per minute at pressure. One got a result of 4.3 air changes per hour, the other 3.9. They were both right. How were they both right, and why did they come up with different numbers? Primarily, they probably just calculated the volume differently. That's what we discussed in class. There is no standard that lists exactly how you calculate house volume. So depending on whether you use interior dimensions, exterior dimensions, how you do your room measurements, how you treat space between the floors, which, again, some people will not count that area between one floor to the other floor. It's still communicating to the rest of the, if it's inside the building envelope, in my opinion, it gets calculated as volume. So, any questions on that one? So, effective air sealing at the joints includes 4 important factors. This is right out of the slides in the lecture. Again, the overall design is important, how the material comes together. Then what product you select. You need to use the right product for the right type of joint. Prep the joint so that you get good adhesion, and then put it in properly. I think that was pretty straightforward. The difference between caulking and sealing, and the main difference really is just that you've got caulking is usually, unfortunately the words are intertwined, but caulking usually refers to a product that's really not designed for effective sealing. It's a product that's got usually a lower cost, lower shelf life, or lower lifespan, and it's used primarily for filling in gaps before painting interior and exterior. And a sealant is a much more high quality product that's designed for proper air sealing or moisture sealing, and they're usually more expensive and have a much longer lifespan. We talked about 5 methods of energy-saving weatherization, and then 5 methods that can be performed on a limited budget, and 3 things you can do that don't cost anything. I would hope at this point in time in the class you can come up with at least 15 or 20 things that you can do on a limited budget, and a bunch more that you could do. That was a free 8 points. You're welcome. So what's the best answer for why a thermal imagery device can be very helpful in building quality control? C, it identifies building moisture issues and thermal bypass. I think I gave half credit for people. A couple people put it determines points of infiltration. Technically, it does determine the final point of infiltration, but not always. It doesn't necessarily tell you where the air is coming in at. An example we talked about where there could be an exterior light on the outside of the house, and that's not properly sealed up, and that's where the air is coming in, but it's coming in following where that wire is chased through the exterior wall, coming down, and it might be coming in through an outlet. But primarily it can help you look for any of the thermal bypasses, which include both air infiltration and conductivity. So the thermal imagery isn't just about infiltration. It'll also tell you when you've got a temperature differentiation due to conductive heat loss. So that's why I only gave half for points of infiltration. Which is most cost-effective and easily implemented improvement to the efficiency of an existing building as opposed to new construction? The answer was B, blown-in fiberglass or cellulose. We discussed the constraints of weatherization and building in an existing, or weatherization work in a new home versus an existing home, and you do have a lot of constraints in an existing home. You can't go in and install under slab insulation. It's probably pretty cost effective to replace the windows or replace the whole heating system. So you've got to do the things that are reasonable and cost effective when you're looking at your energy conservation measures. A list of strategies, which is not a legitimate strategy towards improving efficiency of a typical cold climate residential structure. The correct answer is ensure there's sufficient filtration. We don't want to ensure that there's filtration of at least 4 air changes per hour. We want to try to get down to or below that level. All the other ones are all good strategies. We want to get the lowest U value possible in our assembly. Good passive solar design. If we can do it, it's free. And then trying to do above code, also a good strategy. This one was in the book. We didn't spend too much time on it, but the duct leakage and control, the testing procedure is the ASTM 1554. Remember, the ASHRAE guidelines are, the 62.1 is for ventilation requirements for the whole building. 90.1 is energy performance. It's the ASTM standard that dictates how we do the duct leakage testing. I think that's the one that everybody that was doing the BPI course got right, and the people that missed it, most of them were not doing the BPI course. So that must have been covered in one of those videos that I didn't watch, but I think I've got 2 or 3 left to do. Anyhow, so this picture shows a good example of heat loss by what mechanism? Conductive heat transfer due to thermal bridging. And again, you can see all of the studs straight through. I think a couple people did argue they put heat loss due to insulation deficit. It's a better example of conductive heat loss than thermal bridging, but we'll change that choice of answers if we have that one again. Hint. Which tool or method below is not used in determining points of air infiltration under depressurization? The one is the pitted tube. Remember, that's the tube that's on the blower door itself. But the methods of testing for air infiltration range from the very low tech of just feeling with your hands up to the smoker and thermal imaging. And we also did talk about the smoke machine for the duct testing as well. We tried to demonstrate that. You were all here for the duct blast test, weren't you? Yeah. We tried to demonstrate that in the shop, but our little smoker just does not have quite enough puff to it to make it work. But so this thermal imagery was taken on a hot day in a building under depressurization. It's a good example of what heat transfer, convective heat transfer due to air leakage. This is the one that, with your question before we got started. If it were heat transfer due to moisture accumulation, it probably wouldn't be as wispy, and you can also see it going up the ceiling as well. And just, it is a little bit higher level of diagnostic and looking at the thermal imagery, but you would see a more rounded, if it were from moisture, just via the capillary action. And this you at least, you should be able to see. It's pretty straightforward. They're fairly straight. And
Well, that's hot air and cold house.
that is hot air coming into a cold house. Yes. So it's taken on a hot day. So it's a building that might be under air conditioning. So the hot, moist air from outside is leaking in. Straight volume calculation. This was just a refresher in practice. You guys have done a bunch of these, and again, we're breaking up the spaces into geometrical shapes that we can get a volume calculation of and adding them together, which some houses are easier than others. And again, for most of what we do, if I put a floor system in there and I put a measurement on that floor system, probably calculate it.
And the triangles.
What's that?
And the triangles.
And the triangles, yeah. Don't forget the triangles. But again, it's kind of a real elementary thing when we're talking about any kind of performance testing. Being able to calculate the volume of a building and being able to do it accurately and quantifying how you calculate it is pretty important on your results. So. And then the last one in air sealing, there's a 3/8 of an inch joint between the mud sill of a house and the concrete where the difference in expansion and contraction has caused the sealant to fail. So there's a lot of movement between the materials. What's the best one? The actual answer is a low modulus sealant with moderate hardness. And again, a low modulus sealant is more flexible than a high modulus. We discussed that. And because we've got two materials there that, as stated in the question, a difference in the expansion and contraction rates, they're going to continue to move. So we want to put something in there. We want it to be a sealant, and that's why D is wrong, where it says backer rod along with caulking that has a high movement capacity. We don't want to put caulking in there. Caulking's not going to do a good job of sealing up the air. If we get more than 3/8 of an inch in a joint, then we probably do want to go to backer rod, but we still want to stick to sealant. And we want a sealant that is low modulus, so it does have some good movement. Any of those questions you see, if you see them again on the final and we're talking about air sealing, if there's caulking in the answer as the solution, it's probably not right. Any questions on that one? Did that all make sense? And got it all locked in?
That last one too, and I was really like, create I think backer rod, but then it says sealant, so you think you'd use sealant, and I went with.
Yeah, and I didn't really put those answers down there to make it that hard. and somebody else emailed me on that. They were thinking about it, but Yeah, if I had put down the answer that said 3/8 backer rod, 3/8 of or backer rod with sealant, then that probably would have been the best answer. But low modulus. Yeah. So let's go to. Let me find the next quiz here. Are there any other? Can you think of anything that you guys have questions on that hasn't sunken in yet, or? Again, really, go back through these, and if you haven't gone through these quizzes and seen the things that you didn't get the first time around, go ahead and run through those again. Definitely, you will see a fair amount of these again, I bet.
I think one thing for me that isn't fully clicking, and I don't know why it's not, is the air and moisture barrier placement. Inside, outside, which side of the building. For some reason, I kind of get it, but it's not like. Really
Yeah,
solid.
and there are some guidelines to it, but there's not necessarily the absolute. What I would say is that think of the air barrier as always being on the warm side of the wall in winter. And so you have to think about that a little bit sometimes. In our climate, we're putting the air barrier on the inside of the wall cavity. And we're doing that because we're trying to cut down on that convective airflow getting into our cavity. That doesn't mean that you can't also put an air barrier on the outside of the wall, which is fairly common practice. But if there's a choice and you have to place it somewhere, always think about the warm side of the wall in winter. So in a hot, humid climate, you're putting the air barrier on the outside. You're trying to stop that airflow from getting into the cavity from the outside because it's going to be your drive is going to be different. The challenge comes in talking about vapor barriers, and that's where not all climate zones and not all building assemblies really should have a vapor barrier, and we really could spend an entire semester talking about moisture migration and wall assemblies and how they're affected. And you remember we talked about the WUFI, the wall profile, and running the wall profile. That's because it's kind of difficult to have a very one-size-fits-all rule. But if you're going to employ a vapor barrier, then you have to start thinking about not just the airflow, but also the moisture migration and the humidity and where that moisture is going to go. And if you're going to put a true vapor barrier, class 1 vapor barrier like polyethylene, it's going to stop all that moisture and that vapor, and is it going to be stopping it at a place where it can get down below the dew point and condense? And what the recommendation is for all wall assemblies now, and that's why I think the WUFI profile and really taking each assembly and looking at it independently, I think a lot of building scientists now are more concerned about the ability of a wall to dry than getting so hung up anymore on completely stopping air and vapor transmission. In theory, it sounds great, but you just can't ever always stop airflow in current building conditions. So air barrier on the warm side in winter, and if there's going to be a vapor barrier in the assembly, it has to be placed somewhere that it's not going to create a condensating surface. Is this clear as mud for you now?
A lot clearer.
Yeah. You will hear, the more you talk about it, the more opinions you'll hear, but in our climate, I don't ever recommend a vapor barrier. If you're going to use a vapor barrier in our climate, again, warm side of the wall, because you don't want that, and not, you can't just make it a rule of thumb, but you think about our climate zone, we have very cold winters with very low relative humidity outside, and so the inside of the house during those periods of time is going to be warmer with a higher relative humidity. So based on what we talked about with basic building science, what's that going to create? Significant vapor drive from the inside out. So if we don't have an absolute vapor barrier on the inside, which is very difficult to execute, any moisture that goes into that wall, it has to be able to get out, it has to be able to dry. So what you don't want to do is just trap it inside the cavity. Typical units of energy use intensity, that's pretty easy, 1,000 BTUs per square foot. When we talk about design load of a house, we calculate the design load in BTUs. This house is going to take 80,000 BTUs per hour for heating and cooling. When we talk about energy use intensity, we do it over the course of a square foot, so 1,000 BTUs per square foot. And if you remember energy use intensity, we do that so that we can compare like buildings. The energy use intensity of a residential building is not the same as a university building, is the same as a fast food restaurant, is the same as a hospital. So by comparing it, use energy use intensities, you can compare like buildings. Under the LEED rating system, what are the different levels of achievement? We talked about a couple of the different green building systems. Just know the difference between them and who is the entity that directs that program. You remember USGBC LEED, the ICC 700 is right in the name. It's the International Codes Council. What else do we talk about? Talked about Passive House Institute. There's more. Energy Star. I just mentioned LEED, the USGBC. So know those programs, know the difference. Which of the following is not a unit of rate of change of energy with respect to time? Again, calories per minute, BTU per hour, and kilowatts are all. A therm is an amount of energy. It's not in relative to time. We do our natural gas in therms, so it's how many therms we burn. We talked about heat capacity of different things, heat capacity of fuels. This is kind of just a straight math problem that we did, but talking about the heat capacity of wood. So what is the density in cubic feet? How many BTUs per pound? And then we got the heat capacity of a cord of wood. So if a cord of wood, heat capacity of cord of wood is about 15 million BTUs, and you have a house that averages about 40,000 BTUs per hour to heat, you can kind of figure how much wood you're going to need to cut and chop. And does Sean burn wood in his little cabin, or is he also? Yeah. So he could figure out his design load, and he could know how much wood he should have cut and stacked before he goes into the winter.
He's going to be upgrading to the rocket stove.
What's that?
He's going to be upgrading to the rocket stove. It's better fuel use for that machine.
Oh, okay. Well, you're solving the rocket stove problem then, so he'll be able to. Excellent. Once an International Codes Council code, such as the IEC 2012, it cannot be changed or modified by any state actions. No, we talked about that in basic codes. The state can make amendments to the code. Montana does just that. We talked about several amendments they made, air change per hour reductions. Building codes set a minimum standards regarding occupant safety and health. Energy codes set minimum performance for energy usage, 5 areas that are covered by residential commercial building codes: the envelope, mechanical, service, water heating, lighting, electrical power. There were a couple more easy stuff. This one we had great debates on what is the least expensive power available. The real answer is conservation, but the question, we have to change the wording a little bit so that we don't have debate anymore. You technically can't just buy conservation, so for those of you that were here for the debate, it was fun. Anyhow, what is the least expensive method for I can't even use conserving in the question, but I can't remember how we decided to word it, but the cheapest thing you can do is not use energy in the first place. So that's the point of that one. And then we spent the rest of the class talking about energy conservation. So a hole in an envelope and a pressure difference between the inside and the outside. That's the answer that will result in infiltration or exfiltration. Again, you need a hole. You need some kind of pressure difference, and that can either be atmospheric, it can be wind-driven, it can be from the mechanical system. So you need a driving force for that. Basic question, the cost of the therm, which I don't even know what it is currently. I think it's only about 90, not even 86 cents. Anybody look at the power bill lately? Yeah. Cost of a kilowatt, I gave you a very broad range. It's actually about 6.2 cents. What is ASHRAE 90.1 and 90.2? Those are the standards that apply to both commercial and low-rise buildings, including multifamily residential. The two ASHRAE standards we talked about were the 90.1 and 2, and then the 62.1 and 62.2. So the 90.1 is a reference to energy efficiency standards, and the 62.1 and 62.2 are reference standards for ventilation. BTUs in a kilowatt hour, 3,412, and this is an important number. Remember, if you're going to convert to do an energy use intensity for a building, and you've got a building that does use both natural gas and electricity, you've got to convert them into like units so you can get your energy use intensity. So you've got to convert the BTUs. Which of the following is current residential energy code? That's the IECC 2012. Which of the following statements about efficiency in the context of buildings and systems is most correct? And these are basic definitions of energy and efficiency that come out of your textbook, the Krieger book. So efficiency general applies to a ratio of output to input. So when we talk about efficiency in furnaces and appliances, and we say 90% efficient or 95% efficient, essentially what we're saying is 90 or 95% of the fuel input that goes in comes out in a useful form of energy. So obviously the higher the better. Most of Montana is in climate zone 6. That's good to know, not only for the ASHRAE standards, but for code requirements. The code requirements change depending on your climate zone. The U value of your windows is going to have to be lower in our climate zone than if you get into a more moderate climate zone. The level of insulation. So it's important to know the climate zone when you're looking at buildings in the building envelope. Excuse me. Percentage of total energy consumption used for heating in a cold climate, and it's about 60%. And the balance of that, so what do we call the energy that we use for heating and cooling that changes over the course of a year, that's different within the seasons? Seasonal energy load. And then the rest of the energy that the seasonal energy load is what we talk about when we talk about our heating and cooling loads. And then the predominant balance of our energy that we use every day, the 24/7, 365, is our baseline, remember? Seasonal and base load consumption. So Air Conditioning Contractors of America provides standards software for the following. These are all of the ACA, that's the ACA standards. And those are in the, remember those? Total building demand, load, equipment selection standards, duct design. Those are the manual J calculations, the manual S for selections, and the manual D for duct design. Don't forget those standards. Let's go back to... Any questions on that stuff? Was it like a trip down memory lane for you for things that... It was... It was only a short 15 weeks ago.
Yeah.
All right, let's go through this one. Number 2. So this is one, we did a basic, I had you guys do a basic volume calculation. Gave you the results of the blower door test. So based on that, pretty simple house. It's a rectangle with 9-foot ceilings. So the 11,000 cubic feet. Converting the results of your blower door, you get your blower door in cubic feet per minute, and we're trying to get a result of air changes per hour. So then we've got to convert the cubic feet so it's cubic feet per hour. So we multiply whatever we got for our blower door result times 60, and then we divide that by the volume of the house, and that gives us our air change result. So this one, we got 18.7. How would you describe the air sealing properties of this home? And one-word answer of poor would have been sufficient. But, yeah, it's a leaky house. Advanced wood framing, and why is it relevant to energy efficiency? You guys remember we talked about how buildings are built briefly, and advanced wood framing is a series of techniques that are used, including 2-stud corners, 24-inch on center studs, laying out the windows and doors so they actually fall on stud layout. Basically a series of about 15 to 20 different practices that you can employ that are going to reduce the amount of solid sawn wood in your wall. Why is it important to energy efficiency? Less wood equals more insulation. And so it's not just a wood savings thing. We're not just trying to save wood and save some trees. In fact, in Montana, we like to use trees because it's a pretty good resource. We're just trying to get more insulation in the walls. The 4 primary functions that the thermal envelope has to effectively perform: contain heat, handle moisture vapor, keep out bulk moisture, and contain air movement. So again, we factor all those into design. This question that we did, 2 houses in 2 different climate zones, and this goes back a little bit to your question on the air barrier, vapor barrier, where does it go? One of the home A is in western Montana, home B is in Mississippi. So looking at the DOE climate zone map, and remember we talked about the climate zones and based on heating degree days and relative humidity, should there be an air barrier in the wall assembly, and if so, where should it be located? And yes, there should be an air barrier in the wall assembly, and technically it could be located either on the inside or the outside. It would be most effective on the warm side in winter. If we're going to put a vapor barrier in, it should be absolute, but again, understanding where the warm side of the wall is, if we're going to put a vapor barrier in a house in western Montana, we don't want it on the outside of the wall, because all of our moisture in the winter is going to gravitate in and then hit that vapor barrier. It's on the outside of the wall. It's going to be below the dew point. It's going to condense and turn to bulk. Inversely, in a cooling climate, where most of the time we're trying to exhaust the hot air from the house, exhaust the excess moisture, you're going to want it on the outside of the house. So, and again, huge debate about air barriers, and you'll find, I think, and I would recommend most, that you're better to look at the entire wall profile and make sure that it's got dryability. Worry more about the air barrier first. And unless you're going to get it absolute, a vapor barrier can do more harm than good. Knowing the ACH of a building will give you a better representation of the building's air tightness, because, and I still haven't changed this one. I remember this is when I actually stuck the page number of the answer in there. Nobody even told me that, but everybody seemed to have gotten this one right. So ACH is a better representation of air tightness, because all the cubic feet per minute measurement's going to do is tell you how many cubic feet per minute it takes to keep the building at 50 pascals. And 1,000 CFM on the house we just did, we know that that's about 4 air changes per hour. If we did a house that was 3 times that large and we got 1,000 CFM, they wouldn't be comparable. The larger house would be far tighter. Basic question, just to understand the difference between the two. That's pretty easy. Just K values of thermal conductivity of material. We talked about that during convective heat loss, and this is a simple chart looking at which one had would lose the least amount of heat. So which one would be the least conductive? And when we talk about thermal conductivity and K value, we talk about it per inch. So you've got to factor that into the equation. Same thing when we get into in the next one, when we get into our U value, R value questions and wall assemblies, you've always got to make sure that when you're looking at your values, if it's R per inch and you're using 3 inches of it, then you're getting 3 times that R value. So this one, which would be true of a home in climate zone 1, which is a very warm, moist climate, average relative humidity is over 70%, and average daytime temperature is over 90 degrees. So this is a cooling climate. It's a house where you're going to be running the air conditioner a large part of the time. So no, the heating load wouldn't be higher than the cooling load. The air barrier would be most effective on the outside of the wall. And both the majority of the heat transfer and the vapor drive would be from the outside to the inside. So both the heat and the moisture would be trying to get into the area that you're cooling, which is why B is correct and your air barrier is most effective on the outside. Heat rises. No, heat does not rise, but heat causes the density of air to change, which then makes the air rise, and that's just one of my pet peeves. And if you got it wrong the first time, then shame on me. If you get it wrong again, it's your fault, because I've now gone over that about 30 times. Vapor barrier is required on all building types except in very cold climates. This is false, and again, we had lengthy discussions about vapor barriers, and there is not an absolute. But again, that's why the whole thing in this whole course is really predicated on those little first few things of basic building science that we talk about. How does heat flow? How does heat transfer? How does moisture move? And how does air move through a building? If you understand the physics of that, and you can apply those to a building assembly, a lot of times you're going to be able to answer all of these questions about vapor barriers, air barriers, pretty easily. Any questions on that stuff? And then I think the last, we've got the midterm. Yeah. And then we went over quiz 4. go through. So this question was a long one, fairly difficult. I think all in all, everybody did fairly well on it. We had a couple things on there. And one thing I will tell you and remind everybody, hopefully that they're still listening and not sound asleep at this point in time, but when you get to these questions and we've got math questions with a lot of steps to them, please put your work in there. A lot of times I can see things that are just a decimal move to the wrong spot, and I want to see, more importantly, that you understand the theory behind it. If you make a simple math error, I might give you a little chink on that, but I'm not going to mark the whole question wrong. If you just put one answer down and don't show any of the work, it makes it hard for me to know where your answer came from. So put your work in there. So we talked about R values. We talked a lot about R values and U values and doing those and how to calculate those to do a real conductive heat loss. So this is a question on how to calculate that. And when we talk about clear wall R value, we're talking about that section of the wall that it has none of the impediments in it. We're not taking into consideration the framing. And in this wall in particular, we've got 4 inches of brick, a 1/2 inch airspace, 1/2 inch of plywood, 5.5 inches of blown-in cellulose, and then a 1/2 inch of sheetrock. And the clear R of that, we're just taking those, those R values times the dimensions. So the brick is 0.8 per inch, so 0.8 times 4. The airspace is R1 per inch, and we've got a 1/2 inch of that, so R1 times a 1/2, so on and so forth, and adding those together, and we get a clear R of 24.5. But those are all held together with framing and other materials, so we have to account for that, and we have to add in a framing factor. We added a framing factor of about 20%, which is, we could certainly go and try to calculate each and every stud in the building and figure it out that way, but we use a framing factor and say there's about 20% of that wall is framing. If we're using advanced framing, we might be looking at less than that. We might be 16% plus or minus. And then so the next step of that is figuring what the total U value of the wall is. So we've got to do two things. One, we've got to account for the 20% of the wall that's wood, and wood is 1.5. We gave that section of the wall 1.5 per inch. And there's, what was it, 11 inches, I can't remember, total wall length. I don't remember. I think that's what it was. 4 plus half plus half plus 5.5 plus half, 9, 10, 11 inches. Yeah, so 11 times 1.5 gave us our R value of, 14 point something. I don't know. Converted it to U value, and then convert the original R value to U value. And you take the U value of the clear wall, which is 80% of the wall, so you multiply that by 0.8, and the U value of the framing percentage, which was 20%, so multiply that by 0.2, you get your total. If anybody has any questions on those and still doesn't understand those, please let me know, but those answers are right there in your thing. Do you guys understand that? You understand the difference between clear R? You know, this again is another one of those really long, complicated questions that have multiple steps. And essentially in this, you have to know the difference between R value and U value. You have to know how to convert one to the other, right? Which we should be pretty basic at this point. They're inverse. They're just one over the other. And then you have to understand the percentage calculations. If you've got 20% framing factor, you use that U value for 20%, the other one for 80%. And then the last part of it is the conductive heat loss. And remember the conductive heat loss, and I won't give you this question without giving you some formula information on it, but you should be able to take the conductive heat loss. If you've got the U value of that whole assembly, which we just figured out in that first part of the question, the U value of that wall, including the framing, then you can figure out how many BTUs that wall is going to lose per hour, or this one is per 10-hour period. And that's going to be our heating load. So for that particular wall, Q, which is the heating load, times the U value, times the area, times the length of time, and then the temperature differentiation. Does that all make sense? So total U value that we got was 0.45, 270 square feet, because the wall was, how big was the wall? 9 feet tall and 30 feet long, so it's 270 square feet. In part C, the interior was 70 degrees, the outside was 30, so that gave us a delta T of 40, and then for 10 hours, how much heat loss. Make sense? All right. This was the other big one, and another really big part of the whole course, and calculating our volume and our air changes per hour. Again, taking the house and breaking it up into manageable sections and calculating the volume, especially when you start to get up into gabled areas and finding where the thermal envelope is, knowing how to make those calculations for volume calculations for both rectangles, triangles, and when you do a volume calculation, understanding where you're doing it from, whether it's interior or exterior. Then from that volume calculation and the blower door result, you can figure the air change per hour, right? If you have, so the first part was getting the volume calculation. I'm not going to go through all these numbers, but we came up with a volume of about 19,000 cubic feet. Then we had a blower door test done, and we got 2,590 cubic feet per minute. So we convert the cubic feet per minute to hours because we're trying to get our result in air changes per hour. So cubic feet per minute times 60 divided by the volume of the house, 8.17. That's our air change per hour at pressure. The next part of that is if we wanted to get that down to 5 air changes per hour, what would our test result need to be? So figuring out, going backwards and figuring out the cubic feet per minute. So what cubic feet times 60 divided by the volume equals 5? And just run the math out. Cubic feet times 5 divided by 60, we came up with 1,584 that we need. So look those over. Make sure you understand those questions. I would bet you would see those again. So, any questions on those? So among the options below, what's the most effective way of reducing indoor humidity? Provide adequate ventilation. So again, be careful with vapor barriers. D, reduce showering times. That's not the most effective. And yes, houseplants will put some moisture into the air, but again, following the standards, following the ASHRAE standards is the most effective. What's the baseline in the context of energy conservation measures? So it's defined as the options against which the other options are compared. The baseline definition depends upon the scenario, including the goals of the stakeholders. So in looking at energy conservation measures, you can set the baseline as code and go from there. Say we want this house to perform to code. We want it to perform X percent better than code. But that's something when you're doing energy conservation measures, setting the goal for it. Different type of framing. This is in our basic building structure section. Platform framing versus balloon framing. And the biggest difference, especially when you're starting to get most of the newer construction now you're going to see in residential, and even in commercial, is mostly platform framing. You build one level, you go up. You build another level, you go up. There you still can find a lot of balloon framing where you've got the studs that run the full length from mud sill all the way up to the roof line. It's a big deal when we talk about weatherization in older houses because that creates a direct cavity from top to bottom, and oftentimes those in balloon framing, those will be open all the way into the attic, so you can have significant airflow and leakage up through there. Just a repeat of one question. So what's typical units for an EUI? BTUs per square foot. So, yeah, some of these are just, this is midterm, so some of these are just repeats. We talked about different roof styles. Remember those. Those are on your slides in your presentation. Just a comparison of two houses. We've got two houses. One, they both have about the same, they use about the same amount of energy for heating. One is heated with natural gas and the other with electric. They've got similar size families, similar size lifestyles. What's the most accurate comparison for these two buildings? Right in the question it says they have comparable efficiency. The annual cost for the house with natural gas will likely be lower than that for the cost with electricity. Again, we discussed this back in the very beginning. It's more expensive. Electricity is currently a more expensive form of energy, so therefore it's going to cost more, all things being equal. Just a passive house question. 3 important design components of passive house. Because the houses are so tight, it is required they have a high-performance HRV or ERV. Take significant advantage of passive solar gains. Thermal bridge windows, no. C is the correct answer. So take advantage of the passive heat gains, get rid of all the thermal breaks in the envelopes and windows, and get a very tight envelope at 0.6 or less air change per hour. Those are so it's not B. B is wrong. C is optimized heat gains, thermal breaks. Thermal and bridge double stud wall construction, high efficiency windows and doors. There are more ways than just double stud wall construction to get very, very low air infiltration. So, which is the best of building envelope or enclosing best practices? Correct answer D, a continuous and contiguously aligned air, moisture, and thermal barrier. So the best building envelope is going to have consistent insulation in contact with an air barrier. What best describes a thermal bypass? A thermal bypass, go straight out of your book, this is the Krieger book, thermal energy movement through the envelope. It's any thermal energy movement through the envelope, it's not just air. Significant conductivity, that's a thermal bypass. Any thermal energy movement. So this is another BTU question. A section of wall is 100 square feet in area. The R value is R30. The 70 degrees inside, 20 degrees outside. How many BTUs are transferred through the wall? I'm not showing the math here, but this is the same thing. The total loss is the U value of the area. So you convert R30 to U. So 1 over 30, and then multiply that by the area, which is 100 square feet, times the delta T, which is 70 minus 20, the difference in temperature, and then times 10 for 10 hours. So just a repeat of that last question. When performing the blower door test, what best describes why we take a baseline reading of differential pressure before starting the fan? We're recording the differences between the inside and the outside of the home under typical normal conditions. And so natural pressure differentiations, if the house is experiencing any air movement, stack effect, you could tell today in that house we were in, it was, if you went upstairs, it was significantly warmer upstairs. So there was definitely air rising, not heat, air was rising. And warm air was rising, yes. And so you need to take that reading, you need to take that baseline reading first so that the manometer will automatically adjust for that baseline pressure. Vapor barriers and vapor retarders are tricky, and correct installation should be based primarily on what? Indoor and outdoor climate factors. So again, having an understanding of the climate zone, the difference in temperature from inside to out over the course of the seasons, and in which season primarily, and the difference in relative humidity. So understanding the direction of airflow, and more importantly, the direction of moisture migration is a factor when putting in your air barriers. So both the indoor and the outdoor climate factors. Excuse me. 10,000 square foot building uses 4,000 therms of natural gas, 30,000 kilowatt hours of electricity. What's the building energy use intensity? So remember, if you remember the one slide, we had all of this information on showing the conversions for energy use intensities. The first thing we have to do is get it all into the same unit. And so we've got to get it into BTUs. So one therm is 100,000 BTUs, kilowatt hours, 3,000. The 3.413. It's getting late. It should be 3,412 BTUs, not 3.41. So calculate them both in the BTUs divided by the square footage of the building, and that's going to give you a 1,000 BTUs, kilo-BTUs per square foot. Again, we use our energy use intensity comparing one building to another, and obviously a hospital might be using significantly more kilo-BTUs per square foot than a residence. So just trying to compare like buildings with a like unit. Any other thoughts, pressing questions on what we've covered? That really was a primer, a lot of information in a very short period of time of what we've covered. Anything in any of those quizzes would certainly be fair game. Anything out of the Krieger book, any of our lectures, the slides, which I still think I have to put the slides for the sealant on there. Did I put them on there yet? I will. So again, primarily go back through all your old quizzes, look through the slides. I would not expect you to go back and look through all of the old videos. There's probably 20 or 30 hours worth of Moodle videos on there. So seeing as how you have to watch the BPI videos this weekend, I won't make you do that. Any other questions, comments? Email me early and often if you have questions on what's out there. Don't wait till the 11th hour. Good luck, and yeah, that's it. Enjoy.